Hello. Good morning, guys. My name is Archana Kesavan. I am representing Thousand Eyes here. Some of you are probably familiar with the name. Maybe the T-shirt rings a bell. But if not, we're here for a couple of days and you can get to know us. But more importantly, the reason I'm here is to talk about a research and study that we conducted earlier last year that compares the network performance of the big three cloud providers, AWS, Google Cloud, and Microsoft Azure. So let's start with this. So for the next 25 minutes or so, what we're going to do is I'm going to give you an overview of why we did this study, what was the reason behind the study, the genesis of it, and then get into the data methodology that we use to gather results, and then actually talk about the insights or how did these three providers perform, what was the network performance like, were there any similarities, were there any differences, gotchas that came out, and then we'll stop with some summary recommendations, and we'll have time for Q&A as well. So when we started, before we went on this study, we're looking at how are cloud decisions made today as enterprises. How are you picking AWS versus Google Cloud versus Microsoft Azure? And it turns out that obviously there are a few guiding principles that come into play. Right? You're interested in understanding the global presence of these providers, which is where are their regions located, how many data centers do they have, how many availability zones exist within these regions, and so on. Pricing is definitely a big consideration, and sometimes it has the power to sway decisions one way or the other, depending on how many free credits you end up getting from each of these providers. And then most importantly is the technical fit. Is EC2 or compute available in all form factors that match your requirements? What's the load balancing architecture like? What does the firewall look like, and so on? And that's a really important criteria when it comes to making your selection of these three providers. But then performance is important as well. Who performs better? Do they perform better in certain situations? What should you be aware of? And it turns out that if you do a Google search on AWS versus Google Cloud versus Azure, the first three quadrants that we just discussed, you'll get a lot of information out there. But performance was something that we saw was deficit, was very little information in there. And whatever information was available was not really comprehensive from the perspective of the depth of data that it had, or also they were in snapshots in time. There was not a lot of trend analysis out there. There was very less information on network connectivity architectures. How does the network look like within these three cloud providers, for instance? So when we noticed this deficit of data, we decided to go ahead and bridge that gap by doing this study. And we leveraged our fleet of agents or monitoring probes to gather data. So a little bit about how we gathered this data, how we went about doing this study is, think of, we have what we call as software probes or monitoring agents, right? And they are located in tier 2 and tier 3 ISPs around the globe, and also within each of these cloud service providers. So now these agents are emulating user traffic, and let's call it, by using what is called a test, where they trigger a test that emulates user traffic. Now, these tests inject network packets into the system, and they can understand not just end-to-end network performance metrics like loss, latency, but what we do is also use a highly customized form of traceroute in there that can give you information on network path as well. Something that we wanted to address in here while we were looking at what would be the right mechanism to gather this data was we wanted to stay away from ICMP because ICMP has shortfalls that we're aware of, for instance, that can be rate limited within these hops in the network. So we chose TCP traces to get this data. The other thing that we wanted to be aware of and bear in mind was how to get past around the asymmetry in network routing. And what that means is forward routes are different than reverse routes. So we wanted to make sure while we're understanding performance and gathering these network performance data, we look at both forward path and reverse path as well. So every time a test is triggered, data is collected. And this happens periodically. It happens every 10 minutes. And we collected this data for a 4-week period. We ran the data in July of last year for a 4-week period with these tests triggering every 10 minutes, right? So every time a test is triggered, there's some amount of data that's collected. So what does this data look like? What do we get out of here is end-to-end metrics. So we can understand what the end-to-end source to destination and destination to source, because we are using bidirectional traces here, network loss, latency, and jitter look like. We're also understanding what the network path looks like. I mentioned we use a highly customized version of traceroute that can give us information on the layer 3 hop by hop view of the network with details on where these hops are located, which ASN or AS network they're a part of, and so on. So what this allowed us to do was really understand performance from 2 aspects. One is connectivity architectures to these cloud providers, and also end user performance metric to these cloud providers. So the probes are these agents that I was referring to, which was basically the source or the foundation of our data collection mechanism, are they managed by us. What that means is we have continuous access to these agents. So that allows for any easy detection, or if there were issues with, say, connectivity or local faults, we could eliminate it and replace it with the new agent. But fortunately, in this 4-week period, we did not see anything like that, which was a win. It was a very clean test run for these 4 weeks that we ran these tests. Also, just a point to note that there were no outages in these time frame as well. And what I mean by outages is there's no heavy network packet loss that was seen, or an ISP outage in the network or within these cloud providers as well. So really, for most parts, it was a very clean run. So the data that we here is unbiased in terms of any external factors that was influencing it. Once the data is collected, it's periodically exported to a cloud-based engine that can do trend analysis and reporting, which is how we were able to crunch the data here to come up with insights as to what this meant. Now, just something that I want to note here is that throughout the rest of the presentation, I'm going to be heavily focusing on network latency, because that was one metric where we did see anomalous behaviors and trends. Loss and jitter were metrics that were collected as a part of the test, but I'm not going to talk about it specifically here, just because there was nothing interesting to report. Loss was really minimal, and jitter was as expected, so there was nothing, nothing that really stood out to talk about it. All right, a little bit into test scope. So that was the infrastructure that was used for testing, but what were the different vantage points we looked at this comparison from is we try to understand end user measurements. So we're trying to understand how do users connecting to these cloud providers, what do they experience from the perspective of network performance and connectivity? What does inter-AZ and inter-region measurements within a single cloud provider look like as well? Because we know that redundancy, load balancing, microservices architecture is increasing the communication within availability zones across these regions and within regions in each of these providers. So we wanted to understand that metric as well. And then finally, we did multi-cloud measurements, which is understanding connectivity and network metrics from AWS to Azure, Azure and Google, and all the permutation combinations that exist there. So when it comes to end user measurements, we place these monitoring software probes in 27 global locations. So 27 global locations connecting to 55 regions of each of these providers. So 15 AWS regions were used as in this study, 25 Azure and 15 Google Cloud regions were used here. So there were bidirectional tests running across from 27 global locations to 55 regions. Agents located within these cloud service providers as well, which is how we were able to generate this data. So that amounted to approximately 1,485 tests. These tests were again triggered every 10 minutes for a period of 4 weeks. We looked at inter-AZ measurements, same way through these agents that are pre-deployed within availability zones within a single provider. Now, the interesting thing about availability zones and how they are mapped is that they're really independent per account. So we wanted to take that into consideration. What that means is if I log into AWS with my account login, what gets assigned to me as availability zone could be different for somebody else. So we wanted to take care of that exception, any anomalies that might create. So we had multiple samples running across multiple availability zones within a region. And for this study, we tested this across 4 AWS regions, 4 Google Cloud regions, but we tested only to 1 Azure region, and that's because Azure is still warming up to the idea of availability zones, so we just started with 1 region. Future, we'll be expanding that. And then inter-region was across regions within a single provider, so 15 regions in AWS, 25 in Azure, and then 15 in Google Cloud. And these were all bidirectional tests, again, running periodically. And the final piece of measurement that we looked at was looking at multi-cloud, which is connecting each of these regions from a single provider to another provider. So you can imagine the amount of crisscross communication and tests that were executed as a part of this. So what did this really result in, right? 30 days, 10-minute interval, a test triggered every 10 minutes across those 4 different verticals that we just discussed, end user, inter-AZ, inter-region, and multi-cloud. That gave us about 20 million unique measurements after a month. But we were looking at it bidirectionally, which means we had 40 million unique measurements. And each measurement that we get takes into consideration network loss, latency, jitter, and network path data. So that's 4 attributes per data point that was measurement that was collected. So about 160 million unique data points that we had gathered over a period of a month to come up with these insights and to look at how these 3 providers were performing. So now to the fun part of this. What was the good, bad, and ugly of network performance? Were there similarities? Who performed well? Who won the cloud war? We'll start with the good really here is inter-AZ performance. So there has been a lot of claims we've heard made by each of these 3 providers that inter-AZ performance is always going to be below 2 milliseconds. We've heard that in a lot of talks that have occurred in the past. Those were claims that were made, and what our study showed that with all these 3 providers performed exceptionally well when it came to network latency between availability zones. So AWS in this instance averaged at 0.82 millisecond, and you can see the split across each of those regions that we picked. Azure in the same 1 millisecond range, and then Google Cloud with 0.79 as well. So overall, inter-AZ measurements or performance network latency was really good. It signaled that these providers have robust, well-connected internal architectures. It also gives you an idea of how far apart a data center might be located within a region given the latency numbers. Next year, we'll be increasing the number of regions that we're going to be testing, along with increasing the number of regions in Azure as well. The next is inter-region performance. Inter-region performance is measuring network latency, loss, and jitter within a single provider, but across multiple regions. For instance, testing between AWS East and AWS London, for example. What we noticed, the first thing that stood out, and this is based on the network path information that these agents are continuously collecting, we noticed that traffic stays within the same provider when you're talking about inter-region communication. So think of these agents they're deployed within these providers as compute. So if that means AWS, it's EC2 instances that we are triggering tests across. So communication between 2 EC2 instances go within an AWS network, right? That's the first thing that stood out. And we were able to get a lot of absolute measurements in terms of what the latency looked like. But we were not able to, understand if this was good or if this is, suboptimal performance. So what we did to get a better idea of that is we baselined it with internet averages. So we understood performance from a relative, score. So what that really means is, I'll give you an example to explain this, is if you're looking at inter-AZ measurements for AWS, for instance, between Ashburn and London, we get an absolute measurement value for latency, which is great. What we also wanted to see is that how does that compare with respect to internet baselines going from 2 points in Ashburn and in London outside AWS's network, right? That's how we baselined it, and we got this relative measurement. So we did those performance across those 15, 25, and 15 regions across all of these providers. Now, the assumption is that these providers have really robust backbones. It's not a best effort network, it's a private connected network. So that should perform better than internet averages. And that's how we did this grouping here. So the first two, as you can see, the first two verticals there, you're leaning heavily there in that angle. And what that distribution really means is the number of inter-region pairs that performed better than the internet or same as baseline to the internet is greater, which is good and what we should be expecting, compared to certain regions performed really poorly. There were some regions that were 30% slower than the internet, all the way to the extreme right, for instance, right? So again, from overall, most parts, inter-region measurements were good, but there were exceptions that existed. And one of the example is here in terms of exceptions that exist. So the data that you're looking at here, what the chart is representing, is bidirectional latencies going in from Sydney, Australia, all the 3 providers regions, to Tokyo, Singapore, and Mumbai regions for all these 3 providers. And that's the comparative metric. And the green, the color coding that you see is average and relative to internet baseline. So when you see green, it means that connection between Sydney, Australia, and let's take AWS, the 109 millisecond latency. So AWS latency between Sydney, Australia, and Tokyo is green and 109, which means it's 10% better than internet averages. But if you look at GCP and Mumbai, which is 228.92 milliseconds, that's 30% slower than what you would expect on going across those 2 locations on the internet, right? So there are exceptions that did exist, and it comes into play when you're making these choices on your architecture in terms of how to choose these region pairs. So this can be a guiding factor in terms of what constitutes good performance versus poor performance in an inter-region setup. We'll then jump over to what did end-user performance look like. And just to recap, the end-user performance measurements was done from 27 locations globally to 55 regions across these 3 providers again. Now, the key to reading this graph here, and you're going to see a few more occurrences of this graph, so let me spend a few minutes here explaining it. What you see on the x-axis is the user location. So these are continents from where the user is connecting to this cloud service provider, which is denoted by the hosting region. So the graph on the left that you're seeing here is users connecting from Asia, Europe, North America, Australia, and then South America to US East, Virginia, or to Microsoft's East data center located in Redmond, and the same thing as GCP counterpart as well. And then the one other graph is very similarly, it's connecting to United Kingdom, which is London and Cardiff, is where these providers have their data centers located. And then the 3 colors represent AWS, Azure, and Google Cloud. So what you notice here very quickly is that if your hosting centers are in North America and in Europe, then your latency for users connecting to these hosting centers are really comparable across these 3 providers. There's not really a question of who does better here. They're comparatively all doing really good. No outages, like I mentioned, in this 4-week period, so this was really positive information in terms of performance. But this only holds true if you are connecting to North America and Western Europe, for instance, as your data centers. When you move to Asia, we start seeing a different story, right? Again, the way you read this chart here is, the graph here is user locations connecting to hosting region in Bombay, India. All these 3 cloud providers have hosting regions in Bombay, so it was easy to compare them, right? And the first thing that stands out here is that Google has 3 times the network latency when users are coming in from Europe to India. So if you see the other user locations, it's pretty comparable, but the only thing that stands out here is that red line, which is Google's network latency, bidirectional latency, which is 3 times that of AWS and Azure. The reason for that, it turns out, is that Google uses a very suboptimal route to move traffic from Europe all the way to India. Google GCP, they heavily rely on their backbone to move traffic around. And it sounds like, and it not really sounds like, what data showed is that traffic moves all the way from Europe to the United States to get to India. So let me explain this visualization that you see here. Is the green dots that you're seeing there are representative of our agents located in Europe in those particular locations. And all the way on the extreme right, which is Mumbai, India, that's the region you're connecting to. So these agents are emulating user traffic going all the way up to Mumbai, India, and back. Now, the marked region there towards the very end is a representation of Google's backbone. Those nodes there that you see show that data is traversing the Google backbone, but it also shows the location of where those nodes are located. So all the way from Europe, they go to the United States, they hit California, and then they go over to Bombay. Now, that explains why the latency was 3 times compared to AWS and Microsoft Azure. So what we wanted to do is we wanted to verify and validate that this is indeed right, this is how Google's backbone works. So what we did was we took a look at the fiber connectivity of Google Cloud, right? And it turns out the reason Google takes a circuitous path is because there is no direct route in the Google backbone from Europe to India. So the only way they can go around is to actually go around, right? So this was really interesting. This stood out for us from means of the data that we got. But something else that caught our eye as well from an exception is how AWS was performing. Now let's shift focus, and this is the exact same graph that we saw earlier, which showed performance, network latency, bidirectional network latency from these global locations to a hosting center in Mumbai. But let's focus on those black lines that you see there. Not the actual vertical bars itself. And what that represents is basically standard deviation, right? It shows how much latency can vary in a given period of time. And as you notice, AWS seems to have the largest variation in network latency for users coming in from Asia but connecting to Bombay. Now, this seemed anomalous as well. So digging into the data a little bit more, we noticed that this is a trend that was seen across all AWS deployments, especially in Asia. So what you see here is bidirectional latency variations for AWS for users connecting from Asia to hosting centers in Tokyo, Singapore, and Bombay. And as you notice, the yellow line here is AWS's variation in network latency, and it's so bad in Bombay that your network latency can vary anywhere between 0 to 150 milliseconds. That's pretty high. The reason AWS behaves this way, again, we were able to dig into the network path data that was collected, is because AWS relies heavily on the internet to move traffic. So AWS basically hot potatoes traffic from the user location to their region. What does that mean? A user coming in from Mumbai, for instance, going up to AWS East in Ashburn, is going to go over multiple ISP hops, right? And enter AWS's network pretty far away from, close to the region where it's hosted, so pretty far away from the user location. So in this particular example, users in Frankfurt, traffic from Frankfurt only enters AWS's backbone in Hong Kong, for instance. But that's not the case when it comes to Google Cloud and Microsoft Azure. If you notice here, traffic from the same user location in Frankfurt, they enter the backbone of these two other providers in Frankfurt itself, which means they ride the backbone of these providers longer than how a user who relies on AWS might. And we know that the internet is less predictable, is more vulnerable to it's a best effort network. So you can see variations in performance that exist when you're starting to rely heavily on the internet, for example, which explains AWS's variation in performance, especially in Asia. Now again, this is a snapshot which shows how traffic moves from global users to AWS's network in AWS's region in US East, which is Ashburn. So notice how users from Singapore, they have to go through multiple ISPs, going all the way from Singapore to LA to Texas, and they enter Amazon in either Texas, or they're entering Amazon's network in Ashburn or New York. So it's really close to where the hosting or the data center is. This is completely different than what Azure and GCP do. Same user coming in from Singapore is going to enter Microsoft's backbone in Singapore to go to Richmond, Virginia, which is Microsoft's hosting data center, right? So there's definitely a difference in terms of how you connect to the cloud. So there's a variation in cloud connectivity architectures as such. So this research that we did, it was conducted, like I mentioned, last year in July, and the research is now available online for everybody. We released it in early November, right? And as we know, reInvent is end of November. It happened end of 2018. And AWS, very interestingly, introduced a new service in there called the Global Accelerator. The Global Accelerator, they say, is for improved performance. And what it translates to in simple terms is you pay AWS more money to ride their network to get better performance, right? That's what it means. And that's a cloud trend that we are starting to see. It's what I call the monetization of the cloud backbone. And this is not just specific to AWS. Google made such an announcement as well last year. So Google now gives you two tiers of service, a standard tier and a premium tier. If you pick the standard tier, you're going to hot potato around, use the internet. You're not going to ride Google's network. But if you pick the premium tier, you're going to go on Google's network faster, which means quote unquote better performance, right? So AWS made this recent announcement last year. We don't know how much of an improvement in performance this is going to give, and that's going to be on a use case by use case basis. But this would be really interesting to compare internet performance versus performance through AWS's Global Accelerator. All right, finally, we're coming to multi-cloud performance. So multi-cloud performance involved testing from multiple regions within a single provider to multiple regions to another provider, because there's a lot of communication today in enterprise architectures that's involving multi-cloud. So we wanted to see what this looks like. And as you can see here, jitter and packet loss, and I mentioned this earlier as well, that was not anything significant or interesting that we noticed in terms of trends. The interesting takeaway from a multi-cloud performance angle was how these three providers connect and peer with each other. So they obviously peer directly with each other. And what that means is traffic in a multi-cloud scenario never really leaves the backbone of these cloud providers. So if you're connecting AWS to Google Cloud, you're pretty much going to either go with AWS and then move on to Google Cloud. Now, the interesting note, however, is because AWS does not use their backbone to move traffic, they will push the traffic over to Google as soon as possible, and Google will carry the rest of the traffic. So that's just an interesting detail that we noticed while we were looking at multi-cloud performance. So really that kind of brings me to the end of the presentation here. And what we learned from this was we went into this without any assumptions or not expecting one provider is going to perform better than the other, right? The idea was to learn and find out what the differences are, what the similarities might exist. And what we noticed is that cloud connectivity architectures are not the same. They have an impact on performance, and it's something we should be aware of. Geographical performance varies, especially when it comes to Asia, not so much in North America and Europe. Intra-cloud performance, which is inter-region and inter-AZ performance, for most parts did really well. So that's definitely a positive. And then multi-cloud is a safe alternative, right? These three providers have a symbiotic relationship. So multi-cloud is definitely a good way to go if you're considering that. So in terms of recommendations, what does this mean for enterprises moving to the cloud or starting to rely on these cloud providers is use data as a guiding factor to make your cloud investment decisions. There are a lot of criteria that you need to consider while you're picking your right cloud provider, right? Pricing, geographical location, services availability, but use data as well. Do not discount data, right? Because in the cloud, you can trust, but you always need to verify, and you cannot afford to make assumptions in the cloud because there is no steady state in the cloud. What looks like good performance today might not be good performance tomorrow. All these three providers are continuously investing in their architectures to make it better. So good today might not be good tomorrow, which really brings us to our research vision, right? Since we recognize that this is not a snapshot, this cannot be a snapshot in time, we want to keep doing this research every year. And we want to broaden the scope of this research as well. This year, again, it was the first time we were doing it. We started with the big three. We had 27 global locations, 55 regions. But in the future, we're expanding. We're thinking of expanding it to maybe other providers, maybe more regions. Also understanding and comparing differences in performance for their private connectivity service, right? Which is Express Route versus Direct Connect and so on. So that's something we are thinking of going forward and executing later on this year as well. So it really brings me to the end of the presentation. If you're interested in looking at the report, reading more about it, you can download it from the link there. It's free. If you have questions, hit me up now, or I'm going to be around for the next couple of days and happy to sync up with you. Thank you.
You were there first.
Okay. Hi, Dan Golding with Google.
Hey.
First, I just want to say great present. Don't be nervous because this was a great presentation.
Thank you.
Really impressive. In terms of what you're working on next, would love to see the private interconnect stuff.
Okay.
And I think you may want to consider some different forms of measurement when you do that, and even private interconnect from one provider to another provider could also be extremely interesting. We would love to see that data. And as far as the Mumbai issue, great catch. By the time you run another set of tests, that will be resolved.
Okay, great to know.
Definitely a great talk, Matt Petak here. On the interregion, on one of the earlier slides there, you tossed out a comparison to internet baseline without really defining that too clearly. If you come back and do a future report, I would love to hear a little bit more about how you decided on what that internet baseline was, because that is a whole kettle of worms on how you measure that piece of it.
Absolutely. So the way we did that is these agents we're talking about for inter-region were located within the service providers, but we also have agents that are located outside these service providers in tier 2 and tier 3 networks. So when we picked, say, Ashburn in London, for instance, the measurement that we got, the absolute value was within AWS, and then we used the internet baseline was we picked our agents outside, which is either in, I can't remember which exact ISP it's located out of for that region, but we looked at Ashburn and then another agent in London, and that's really what we meant by internet baseline, which was, it wasn't going within AWS's or Amazon's or
right,
Google's
but where
network.
the selection of your agents is, you're measuring specific backbone tier 2 connectivity, and that's not really internet average. So reflecting that out and saying, okay, this was a CenturyLink to a Cogent measurement point. you're looking at two specific providers there. Unless you have enough data points to really get a good aggregate, you're actually looking at a separate set of measurements, which is useful, of provider-to-provider connectivity, but generalizing that as an internet baseline might be a little
Might not be
misleading.
comprehensive.
Yeah.
Fair enough.
But
Okay.
good talk. Thank you.
Great. Thank you.
Hi, my name is
Hi.
Evan Moore from First Light Fiber Corporation. I'm very curious on this 10-minute sampling interval that you used in your study, and what discussion or consideration brought you to the 10-minute interval. My first response is 10 minutes is an eon. So I'd like to hear that.
Well, there's nothing really restricting us from, reducing this interval all the way up to 1 minute as well. To be honest, we thought, well, do we want to test it once every hour or once every minute? Is there going to be much changes once every minute, because we were measuring over a period of time? So we just picked 10 minutes as, a point that worked out well. It is possible that we can reduce that in the future as well.
David Zimmerman, LinkedIn.
Hey.
Hi. So glad to see that Azure wasn't worst of most of the categories. That was positive. +1 on the private connectivity part, ExpressRoute, and if you're not aware of it, ExpressRoute Direct might have different performance envelope, so you might want to look at those somewhat separately, or whatever they're renaming them to. But most importantly, did you do these tests over IPv4, IPv6, or both?
It was IPv4.
Do you have any plans to include IPv6 for 2019?
It's possible. We haven't really thought about it right now, but our agents are in V4 and V6 environments as well, so that is something we could consider. I'd like to touch base with you later on to see if there's specifics with V6 you're looking for.
Sure, be happy
Okay.
to talk.
Cool. Any other questions? All right, I won't stand in the way between lunch and you guys, so thank you so much for your time.